Hello and welcome. Introduction. Now this is part 2 of the TM4C123GH6PM general purpose timers. I'm going to assume that you have watched part 1 of this series on the TM4C123GH6PM general purpose timers. Okay, so in part 1, I was trying to blink the blue LED, let me get my pointer, blue LED on the Tiva C series LaunchPad board using the TM4C123 general purpose timer. And we observed and measured with the aid of a logic analyzer the blinking or the flashing rate, and it happens to be 320.05 milliseconds. Now, this is far short of the 1 second interval that was calculated. So, in this video, I'll show you how I resolve this discrepancy. The Kyle Microvision startup file. Now, the 1 second interval that was calculated assumed that the system clock is 16 megahertz. Now, here is a partial schematic of the Tiva C series evaluation board, and I've taken this from the user manual, and the schematic shows a 16 megahertz crystal that is used. So I assume that the system clock is 16 megahertz. I soon discovered that the system clock is set by the Kyle Microvision startup file. So this is the startup file, and it's called system_TM4C123.C. And if you double click on it, on this file, you can view the contents of that file. And this is the file name, system_TM4C123.C. Now, it is this file that sets up the system clock to 50 megahertz. Now, the 320.05 milliseconds on-off periods that we seen earlier, basically they are consistent with a system clock of 50 megahertz. Let's analyze this. So the system clock assuming to be 50 megahertz, and the time load value would be 16 million. Now, this 16 million, I've got it from the init timer function that was used in the previous video. And it's this statement here that I highlighted here. This is where we set the time interval to 16 million. And this is the hex equivalent of this. So it's 00F42400. Now, first off, we need to calculate the system clock period. And we do this by using this equation. So the system clock period is equals to 1 divided by 50 million. This 50 million is from this 50 megahertz. That would give us a 20 nanoseconds. Now the time period, the time interval equation is this here, this equation here. So it's load value multiplied by the system clock period. So if we substitute these values into the equation, so 16 million for the load value, multiplied by 20 nanoseconds for the clock period. So 16 million multiplied 20 nanoseconds, that would give us 32 million nanoseconds. And if we do the conversion, we'll get a 320 milliseconds as seen earlier. TM4C123 series microcontroller clock. Now, before I go any further, I'd just like to remind the viewers that I'll be referring to the TM4C123GH6PM microcontroller data sheet and the Tiva C series TM4C123G LaunchPad evaluation board user guide. This is a diagram of the clock tree of the TM4C123GH6PM, taken from page 222 of the datasheet. We'll start off by looking at the system clock. Now, move over to the left-hand side. We have the main OSC. Then we have the precision internal OSC. Then the internal OSC. And the hibernation OSC. Now, and then we have these control bits here: MOS, CDIS, IOS, CDIS, OSC, SRC, XTAL, PWRDN, DIV400, bypass, SYST, SYSDIV, and then USE, SYSDIV. Now, all these names here are control bits within the clock configuration registers, RCC, and the clock configuration register 2, RCC2. Clock configuration registers. Let's take a look at the clock configuration registers that are closely related or associated with the clock system. Now, here is the run mode clock configuration register, RCC. That happens to be register 8. And let's take note of the control bits that was mentioned earlier. So we have the MOSCDIS bits here, control bit here. And then this is supposed, the bit 1 here is supposed to be the IOSCDIS, but for some reason it is not printed. I don't know why. And then we have the XTAL. Oh, by the way, MOSCDIS is the main oscillator disable bit. Then we have the XTAL. This is the crystal frequency. And then this is the OSC SRC. This is the oscillator source bits. Then we have the BYPASS or the bypass mode bit. This is the PWRDN or the power down bit. Then we have the USESYSDIV. This is the U system clock divider. And then we have the SYSDIV. This is the system clock divider. And here is register 10. This is the run mode clock configuration 2 register, or RCC2. Take note of this control bit here, DIV400, and also the OSC SRC2, and then the BYPASS2, and then the PWRDN2. The Tiva C LaunchPad operating frequency. So this is the diagram of the clock tree of the TM4C123GH6PM. We've seen this earlier. Okay, so let's focus on the PLL. All right, let's look at the input here. So the input to the PLL can be coming from the main OSC, or it could be coming from the precision internal OSC. Now, this is all depending on the control bits here in the OSC SRC. Right. So the purpose of the OSC SRC is to select one of these as the input to the PLL. Now, these bits here, the OSC SRC, can be found in the run mode clock configuration, or RCC register, and the run mode clock configuration 2, or RCC2 register. Assuming the OSC SRC bits are set to 0, 0, then the main OSC is selected as the input to the PLL. Okay, so next we consider the DIV400 control bit here. Now, this control bit, the DIV400, is found in the run mode clock configuration 2, or RCC2 register, and the DIV400 control bit is this bit here, the bit 30. Now, when the DIV400 bit is set to 0 or cleared, the PLL output, which is 400 megahertz, is divided by 2 and resulting in 200 megahertz. Now, next, the bypass control bits here is set to clear, and the 200 megahertz is selected to go through. Okay, so when the bypass bits here are set to 0 and the USES YSDIV bit is set to a 1, all right, this path here will be selected, and the 200 megahertz that we've seen earlier would be divided by 4, which is determined by the divide by 4 is determined by the SYSDIV bit. All right, so from table 5-4 of the datasheet, if we look at the datasheet and under the column of SYSDIV, if it's set to hexa 3, the divisor would be 4. Hence, if the 200 megahertz as seen earlier is divided by 4, the result would be a 50 megahertz. So as mentioned just a few moments ago, the 200 megahertz divided by 4, the result is a 50 megahertz. And this is how the system clock is set to 50 megahertz for the Tiva C series LaunchPad board when using with the Cal Microvision IDE. So we have seen how the system clock is set to 50 megahertz. Let's calculate the load value for a 50 megahertz system clock. So here is the equation for the time interval, which is time interval equals load value divided by the system clock. If we rearrange this equation, we'll get load value equals time interval multiply system clock. Now, the time interval that we want for our LED blinking rate of 1 second, we set the time interval to 1 second. Then the system clock, as seen earlier, is 50 megahertz. So if we substitute these values into this equation here, we'll get load value equals 1 multiply 50 million, which is the 50 megahertz. And that will give us a load value of 50 million. The program. Let's revisit the program that we used in the previous video to blink the blue LED on the Tiva C series LaunchPad board. Now, please watch the previous video for the detailed explanation of this program. Please refer to the link of that video in the description. Okay, so this is the main part of the program, and please take note of this two functions, init GPIO and the init timer, and also the toggle LED function. And here are the two functions, the init GPIO function here and the init timer function. And draw your attention to this load value of 16 million that we used in the previous video. Come back to this line of code later on. And here is the toggle LED function. Okay, so let's look at the init timer function. Now, using the information that we have discussed earlier regarding the system clock, we need to change the load value, which I have done so here. I've changed it to 50 million decimal. In hexa, it would be 002F8F80. Now, this load value here will give us the 1 second time interval needed to blink the blue LED at 1 second interval. Demonstration. Now, for this demonstration, you will need the Tiva C series LaunchPad board connected to your desktop or your laptop. Okay, so we are in the Cal Microvision IDE. I've uploaded the code here, and let us briefly go through it. So I declare my functions here. Here is my main function. in the main function, I have init GPIO, init timer, and then there's a while loop with the toggle LED function. And here is the init GPIO function, and here is the init timer function, and the last but not least, the toggle LED function. Alright, so basically the code is the same as the previous video, except the load value, as mentioned earlier in the discussion, I've put it at 50 million. Now, instead of using the hex value here, I've chosen in this demonstration to use 50 million decimal. Alright, that's the only difference between this and the earlier discussion. Alright, so let me just build the target. And I got 0 errors and 0 warning. Let's go to the download. But before the download, let me just show you I've got my Tiva C series LaunchPad board connected to my laptop. And I'm going to do this first demonstration without the logic analyzer. Alright, so let me just download the code to the board. The picture will go off for a little while, but anyway, I'll do this. So go to download. And it says programming done, verify OK. So let's bring the board up, and let me just do the reset here. And as you can see now, the blue LED is blinking. Alright, this time it looks more of a 1 second interval in between on-off state. And so let me just hook up the logic analyzer and measure the actual output. Okay, so I've got my Tiva C series board connected to the logic analyzer. Let me just take the camera and show you where the logic analyzer is. Here's my logic analyzer. Alright. And let's go back to the board. Alright, and let's now pull up the logic analyzer software. And I've got, this is the output here. Let's zoom in and look at this. Alright. So zoom in and we see it is 1 second on, and let me zoom out, and then we just measure the off state and see what it's doing, and it's also measuring 1 second, and zoom in. So the off is also 1 second, as you can see. Alright, so let's zoom out. So the output from the logic analyzer confirms that the time interval for the on-off state is 1 second. Okay, that's it for this video. I hope you have found the video useful. Thank you for watching, and I'll see you in the next video. Bye.